I think that's just because the internal implementation of the compiler. Yeah, some compiler doesn't support full data types. Yeah.
Yeah, well, so, you know, in addition to those kinds of issues, in practice, as you see deployments of accelerated primitives for convolutions of various different operations, naturally there creep in subtle discrepancies in the way they work, you know, whether they be software or hardware implementations. So there's always going to be this natural difference between operator implementations. That's not necessarily a problem for machine learning. So, you know, if you look at the way neural network architectures are trained, they tend to be quite robust to this. And I think, as Ralph was covering earlier, there are lots of different ways you can recover that accuracy loss as you're running these networks, particularly with retraining. So over time, you know, I'd hope that specific implementations work with the training framework such that you don't have issues with differences between the operator implementations anyway. So.
And wrong, he's right.
So what's your, this is a good microphone, I could whisper. What's your point-wise operations? So convolution is pretty easy. It's an average across multiple points. An alt-wise add is a point-wise combine. That's already, batch norm is really sensitive. Anytime you introduce any kind of bias, you know, what's your rounding mode? What's your rounding mode? What is the rounding mode that the hardware supports? Is that the same rounding mode that, of the hardware that you trained on? What if that rounding mode is just slightly different? Boy, huge impact on accuracy. And can I even, you know, if I have hardware, and I said earlier, you can retrain for anything. Yeah, retrain for a lot. But if you have hardware that has the wrong rounding mode, that introduces some kind of bias, you won't even get the network to converge. So I find that point-wise operations are really picky, sensitive, whatever you want to call it, right? And watch how, I don't know, the details, that was my point earlier, the details of the data path of your processor, whether that's the training processor or the inference processor, needs to be fully captured. And I didn't think the frameworks don't even, the framework guys don't, or the network exchange format guys don't even understand what this means yet. You know, we should actually have someone come by and give a good presentation on training of networks and sensitivities to, you know, especially the element-wise operations to the network exchange format guys and also to the processor guys. Right? That's sort of it's a framework exchange format, the data science training guys, and then the processor guys, whether inference or training, they need to all come work together on this one.
Just to your comment on the network format, there has been some work on you know, bfloat and flexpoint and these kinds of things. I was wondering specifically on ACAP, how is it? You know, if you can share, what is the numeric format that you are looking at, and you know, is it?
Yeah, it's not publicly announced, so early October they will say so, but I'll say that it supports floating point and fixed point. And then we have basically, especially for fixed point, we have a really good quantizer unit, and all the magic is in that quantizer unit. But it'll be floating point and fixed point and different vector lengths depending on data type.
And is that also in the, and of course the FPGA fabric can.
The FPGA, yeah. I mean, yeah. So I personally like bfloat. Still thinking about that. So basically, because I said earlier, right, when we said training, right, we actually train in floating point, in a floating point container, but we model the effects of quantization and biases and so on within the floating point number representation container. So what is bfloat? Bfloat is, you know, it's in fewer bits. So I can represent a bfloat in a regular floating point number. Yeah. So that's sort of, or is it inclusive containment or whatever you want to call it. So I like it for that. And yes, the answer is we have, with the FPGA fabric, we can do any precision and any quantization mode and any biasing mode. The FPGA fabric is most flexible. Right? Now, it's not as dense as what if you build a highly optimized vector processor can do. And if you also build in some architectures around memory formats as they occur in in machine learning problems. If you want to build the ultimate processor, you look at building dense two-dimensional, even preferably three-dimensional systolic arrays of MAC units, and you have really highly specialized interconnect memory structures around that. But we don't go to that extreme. We don't specialize. We build FPGA fabric, and now we have this software engine fabric that gives us a bit more density, but we're still pretty flexible because this stuff just is different for every network, and new operators get invented, and people find better ways of doing rounding modes, and I don't know. It's still very early and dynamic, this field, so I wouldn't go and overly commit and specialize.
Cool, thank you.
I would like to go back to the deployment model. Both Rob and Mark, you mentioned in your presentation this morning that you use converters to convert from the various frameworks into the DLC, the deep learning container. And Rob was mentioning that you can read the models from the various frameworks. Are these offline converters, so the applications need to be aware, or are you running them on the device?
Well, so for the ARM and N software stack, the converters are actually online today. So what you do is you generate the TensorFlow PB file or ONNX file as an offline step, and then that's fed into the ARM and N runtime on the target platform and is converted to this intermediate form that we typically just hold in memory rather than storing it out. And yeah, that's the flow we're using.
For the Snapdragon Neural Processing Engine and the SDK, there are tools that are offline that are provided. So you can take the protobuf files, for instance, and then do the conversion to the DLC, and then you just have the DLC that you have to pass into the application.
So imagine that we have a Snapdragon-based edge device, and then we have another device based on the ARM&N, and we want to deploy the model and have it executed on the device. The orchestration software that is provisioning the edge nodes and is deploying the model and the graph on the device. Does the orchestration model need to know and run your offline converter before deploying? So do we need knowledge of each specific target edge device?
I think the question's at the wrong level because you're looking at an application that would have one of the other built into it. So you'd have an application built against ARM&N, or you'd have an application built against the Snapdragon Neural Processing SDK. And then underlying it would use each of those. The workflow would be different. I'm trying to envision a platform that has either of those libraries on it.
What I'm envisioning, and I may be wrong, is today we have a cloud of nodes in the data center, and we can deploy applications. We spin off VMs, and we can run applications there, and we have virtualized GPUs. So I'm envisioning an edge of devices that we can provision with an orchestration system, and we can deploy and we can spin off nodes at the edge, and we can then deploy the applications that would not be built in.
Right. Well, so in practice,
is it a wrongly placed question? Does it make any sense?
I mean, a potential eventuality for this is that we do reach this common intermediate form that allows us to represent across one or more inference engines the same network with sufficient information, either as side channel information for specific accelerators or specific processes to make the performance better on different targets, or and also containing a more generic form that allows you for the portability across multiple different implementations. I imagine that as this discussion evolves, that is the kind of thing that we would get to. So.
And
To your comment, I mean, that is sort of the whole initiative with Lenaro, is to be able to bring the opportunity for that kind of consolidation to come together
Yes.
and to explore, you know, how do we get to that point? So,
Yes.
yeah, we just don't have that today.
yes, and I'm thinking of what Jamie presented earlier this morning, where you were saying, yes, thank you. Is it an NVM that runs first, and then TVM compiles for the backend? Is this right?
Yeah,
So
yeah, NVM is graph level.
yes. So can we think of a hybrid approach where from the orchestration, when you need to deploy the app or the workload at the edge, you use for example, use an NVM to do an offline optimization of the graph that needs to be deployed, but then you don't do the TVM part, but you build for the Onyxify API, and then you deploy that. Can a hybrid approach between the two options?
So first of all, the compile time isn't really very long, right? So the whole online versus offline is not a compile time question. And of course, you get an FPGA with place and route in the mix, and yeah, it's only offline compile, it's never online compile. But in general, compile times is not the problem. And separately, why can't you pre-build for multiple different targets and just pull up the binary for whatever target is appropriate? Actually, I'm a big fan of runtimes, doing these decisions dynamically, but you need more information on what's my constraint. Is there a guaranteed rate throughput? Is there a load balance? Is there a latency guarantee? I don't know. You need more information. You need more constraints. I don't know what you're optimizing for, but in general, compilation is so fast. You can just and these network models aren't very big. Unless you're really changing your parameters for cloud versus edge, as in cloud I'm running in floating point, and edge I'm running at Xilinx 1-bit. I don't know. You can pre-build all this stuff and just have the runtime pull up whatever is appropriate, and maybe even compile one layer at a time, and even have the runtime distribute across, I don't know, 10 different fabrics dynamically. I don't know.
Yeah, so you know, one of the problems you deal with when you're deploying on a mobile platform is, of course, if you have multiple different intermediate representations, then the binary weight for an APK distribution can be prohibitive. And that's one of the reasons why graphics drivers standardize on SPIR-V and other intermediates that mean you can target one fixed intermediate form. So yeah, so maybe not. Sometimes that's an intractable problem. But you know, one of the things you can look at is, okay, well, can we standardize part of this problem rather than all of it? So as long as weights are, which are the majority of the data that you're shipping around with the network, the representation of the neural network, can you standardize on the weight formats, but have different representations of the network architecture and the scheduling order, maybe in an instruction form, maybe an intermediate form, and that way you control the binary size, but you have the optimization for specific targets. And that's a potentially interesting practical route out of this. So.
There was another part to this question. That was this whole, what do you do in the NNVM versus TVM portion of the compilation phase, right? I say be careful, because the NNVM phase isn't all that architecture independent. There's actually architecture dependent information in there already, so you got to be careful. I do them both. Yes, they're separate things, but I wouldn't do one generically and then one finalized, and so don't think along those lines. Think really squeezing out the most you can do for any given fabric.
That's true. For NNVM, actually, the optimization can be divided into two parts. One part is target agnostic. Another part is target specific. So this target specific optimizations, we will probably need to take care, I think. Yeah.
My comment was that even what you think is target independent really isn't all that target independent. I can squeeze out more efficiency if I, even when you're in the NNVM phase, I'm aware of what target I'm compiling for. And at the same time, I don't think the compilation is that expensive, so I might as well just optimize all the way.
but then you need to have upfront deep knowledge of all the targets. And you may have a pool of 100 different IPs out there, like the DLAs that you were mentioning.
Yeah, pre-built for all of them have the runtime dynamically decide. Right? The thing that makes the network big is the parameter set, not the how you compile a graph for a particular processor. Pre-build that graph for multiple different processors, binaries, and keep your binary so the binary doesn't grow that much. It's the parameters that really are large.
Yeah. So if we can get to the point where we're using common development environments and common tooling environments for this kind of deployment, then that gives us the opportunity to get to this compile for all interested targets. So, you know, all devices supporting the Linaro ML deployment flow would make that kind of thing possible. So.
I was just going to sort of disagree, although obviously that's extremely bad form. But so one of the reasons that LLVM has the opportunity to do target-independent operations is that the language, that the IR language, is expressive enough to give you different ways of doing things. So you might do something to two different IR nodes because they're genuinely different choices. If you've not got a lot of expressibility in your overall language because it's a data flow graph with a node X type and a node Y type, then you don't have that much space to do target-independent things. So it kind of depends on how big the space of changes you might want to do in whatever format is, as to whether there is genuinely a split between target-independent and target non-independent choices that you would make there. But then I would also come and say, if you're trying to ship a generic piece of software to a large number of people, build it for every variant is not possible. It's not even possible for Xilinx. And there probably is a space. So that there has to. When you look at the bigger ecosystem, where you say, well, actually, if I'm going to ship something in the App Store, it needs to work on every device then I really completely understand the reason why in the post-download phase, you want to go optimize for my device.
Mm-hmm. And the intractable one there is for devices that don't actually exist yet.
Yeah.
I want my application to work on those in future.
Yeah, so to me it makes a lot of sense to have an online optimizer, which is one package that I've downloaded that I update infrequently, and an intermediate format that lasts forever, and so I have backward and forward compatibility, and then download the model once in whatever application. When I go to Expedia and I download my snap the bed bugs in my hotel neural network, then it gets optimized, once for you.
Yeah, the challenge is that you've got to now embed that JIT compiler, for instance, inside the application, and in the Android APK environment, that's generally intractable. So if you could make it a platform library and say that you could encourage Google to provide an extensibility API, an NN API, and then you could pass in some kind of IR that would then be able to generate to a particular architecture on that device, now you can do the kind of thing you're describing.
I had a great pleasure in asking Ta for misleading questions. A disclaimer, this was not prepared. These poor guys were not really aware of the questions. We have been asking the questions live. So thank you very much for having accepted to play this. And please, a big thank you to our guests.
And I would like to actually offer a big thank you to Andrea for putting all this together and all the work. It's been great. Thank you. Really appreciate it.
My pleasure.